Okay. Now I heard it. It said
Yeah,
recording in progress.
right. That's the same disembodied voice that says your call is important to us.
Exactly. All right, maybe let's give it 1 more minute. Is that reasonable to then get started?
Sure, your colloquium. I mean, when people are still coming in frequently,
Yeah.
suggest that. Oh yeah, there's awesome in the waiting room. We
Yes,
can't start without her.
exactly.
Hi, Judy.
Hi, awesome, and I saw you in Erterman. When was it? Tuesday. I was having coffee at the Pen Quotidien, and I saw you guys walk by, and I waved at you.
Oh, I didn't see it.
Yeah, well, that's all right. You can wave back now.
All right. All right, maybe I'll at least get started with the introductions. Hello, I'm Gizem Karali. I teach at Pomona College in Southern California in the United States of America. And today, it's my honor and pleasure to introduce to you Professor Judith Grabiner, the Flora Sanborn Pitzer Professor Emerita of Mathematics at Pitzer College, which is one of the sister colleges to my own institution. Grabiner got her degrees from University of Chicago and Harvard University, and she has taught at Pitzer College for over 30 years. And most recently, she technically got retired, but we are grateful that we still get to see her and benefit from her throughout ever since then. So she is still in Claremont, so we're very lucky to have her. Now you can read all about her from her Wikipedia entry to learn about the basic outlines, and in fact, I can sort of put it in the chat if you would like. But I can tell you that Professor Grabiner is a respected and accomplished historian of mathematics who's renowned not only for her scholarship and her publications and her research, but also for her teaching and her expository writing. And she has earned several important awards in each of these areas. Besides her original research focused on 18th and 19th century European mathematics, Professor Grabiner in her work emphasizes the impact of mathematics on human civilization and the human, cultural, social, historical, philosophical dimensions of our discipline, along with its immense power. So that's all I will say. Without further ado, I will mute myself and give you Professor Grabiner.
Yeah, okay. Thank you, Gizem, for that very nice introduction. And thank everybody here for inviting me to give this talk. I didn't realize I could give a talk in Turkey from my own study here. So this is the title. I want to start this talk with an introduction. Well, Hank, excuse me. All right, why is it? There we go. Okay, there will be technical problems. There always are. But anyway, first an introduction. So I'm going to start by asking what is space, and I'm not going to answer the question, not outer space, but what we and all the objects around us are in. Does space exist? And if it does, how can we find its properties? I'm going to talk today about the history of these questions, philosophical as well as mathematical, because it turns out that the entire universe is involved in these questions. Mathematicians like Newton and Descartes, and philosophers like Immanuel Kant imagined a space of 3 dimensions, and that was a space according to Euclid. When we use terms today like truth and proof, we're going back to Euclid. For 2,000 years, Euclid's elements of geometry seemed to prove truths about geometrical objects, and thereby to achieve certainty. Certainty, that's a pretty good thing to achieve. For the philosopher Aristotle, the truth and certainty of what he called a demonstrative science, like geometry, a demonstrative science, the truth and certainty come from how it's put together, using logical deductions from self-evident assumptions, from clearly stated definitions, and from previously proved statements. Euclid was probably looking over his shoulder at Aristotle's criteria for a demonstrative science when he, Euclid, was writing his Elements of Geometry. And this is a key point, many important later thinkers believed that other subjects might come to share the certainty of geometry if they could be given the same logical form. So Descartes, for instance, said that if we start with self-evident truths and then proceed by logically deducing more and more complex truths from these, why then, he says, there's nothing we could not come to know. Descartes had followers. For instance, Spinoza, the philosopher, wrote a book called Ethics Demonstrated in Geometrical Order, with explicitly labeled axioms and definitions. And I will read you just one of his theorems. God, or substance consisting of infinite attributes, necessarily exists. He closes the proof of that theorem with a QED, which is to be proved. The influence of the Euclidean ideal on science is clear from Isaac Newton's great work, Mathematical Principles of Natural Philosophy. As you can see from this slide, Newton called his famous 3 laws of motion axioms, and Newton deduced even his law of gravity in the form of a theorem. The United States of America has a history that begins with the Declaration of Independence. And the Declaration of Independence is another example of an argument whose author tried to inspire faith in its certainty by using the Euclidean form. It starts, the author Thomas Jefferson, later president of the United States, and who knew more mathematics than any other president we have ever had, more of the mathematics of his time than any other president we've ever had. He starts his argument with an axiom. We hold these truths to be self-evident, that all men are created equal, and that since the British government has failed to secure human rights, the people have the right to get rid of it and set up a new government. The actual Declaration of Independence at the bottom of this slide, you see, sounds like the conclusion of a logical argument. It begins with therefore. In a number of countries that have declared independence since, for instance, Liberia, Czechoslovakia, Vietnam, followed this logical structure of the American Declaration of Independence in their own. Okay, so that's the introduction. And for the first half of the actual, I have a sentence to read before the introduction. In science, politics, theology, and philosophy, the idealized Euclidean model of reasoning has shaped conceptions of proof, truth, and certainty. So that's the introduction. The first half of the actual talk, I want to look with you at Euclid's Elements of Geometry, at the idea of Euclidean space, and some important related ideas and their influence. But we're also going to see that there's a problem with this model. And in the second half of this talk, we'll see that the problem and its resolution have produced something else, a non-Euclidean world. And this break with the past has had an impact comparable in its power and influence to that of Euclid. Okay, so here let's go with part 1. Here are the postulates, the basic assumptions of Euclid's geometry, meant to be the minimal set of self-evident truths from which all of geometry can be logically deduced. Well, postulates 1 through 4 are pretty straightforward. I think you recognize these as the rules for Euclidean construction and transformations. But look at number 5, Euclid's so-called parallel postulate. Well, you'll notice immediately that it doesn't mention parallels at all. That one's complicated, so I think we better draw a picture. Postulate 5 says this: if those 2 green lines are cut by a third line AB, such that angle A and angle B add up to less than 2 right angles, then the 2 green lines eventually meet on that side. Now, my students would always say to me when I'd talk about this, that's not self-evident. You've got to draw a picture even to understand what it says. Well, the ancient Greeks agreed with my students, and that is the problem that I mentioned. Well, okay, if this postulate isn't self-evident, then maybe it can be proved from the other postulates. Well, the Greeks tried to do this and did not succeed. And so then, following the Greeks, did some of the greatest mathematicians in the medieval Islamic world, all immortalized here on stamps from showing their international influence. And the mathematicians of Europe well into the 19th century followed the work that the Greeks and the astronomers and mathematicians in the Islamic world had carried out. We know, for instance, that Al-Tusi, who was on that previous slide, that his work was known to Wallis and Sakari. And these are big guys in European mathematics of the 17th and 18th century. And they're all trying to prove Euclid's fifth postulate from the others. Well, what progress did they make? One of the things that the Greeks proved right from the start is that Euclid's postulate is logically equivalent to the uniqueness of parallel lines. Given point in the plane, there's only one line through that point. There can be only one line through that point parallel to a given line. That's a common alternative postulate. You find it in many textbooks, but this is not Euclid's. Okay, Euclid defined parallel lines as lines in the same plane that never meet. And without using postulate 5, he proved a bunch of things, including that parallels can be constructed. That's why I said there is only one parallel. He doesn't assume that there are parallels. He proves that you can construct a parallel. It's based on the theorem that the exterior angle of a triangle is greater than either opposite interior angle. But the main point is that getting parallels, proving that they exist, does not need the parallel postulate. But he does need the parallel postulate. He uses it extremely rarely. What do you need the parallel postulate to prove? Well, this theorem. If two lines are parallel, the alternate interior angles like angle 3 and angle 6 are equal, and the corresponding angles like angle 2 and angle 6 are equal. From this key theorem that I've got up here, Euclid proves a large number of things, not only the uniqueness of parallels, but many other theorems about parallel lines, like that they're everywhere equidistant. Okay, so that's the logical problem in Euclid's geometry. Now let's go back to space. Well, Euclid himself doesn't mention space at all. But starting particularly in the European Renaissance, philosophers get into the act and they talk a lot about space. So let's look at what they say about space. Space is infinite. Space is homogeneous. That is, it's the same in every direction. And every point in space is just like every other point. And that is the space that Euclid's geometry happens in. And the idea that space must be the same in all directions doesn't come from mathematics. It comes from philosophy. And it comes from a thing in philosophy called the principle of sufficient reason. Okay, this is a statement of the principle of sufficient reason, and it's going to sound, when I just read it, trivial. For everything that is, there's a reason why it happens as it does and not otherwise. Okay, very old. It's as old, as least as explicitly stated as Archimedes, and he used it, Archimedes, to prove that a lever with equal weights at equal distances from the fulcrum must balance. Well, why must it balance, Mr. Archimedes? Why not? Because the principle of sufficient reason says there's no reason for it to go down to one side or the other, and therefore it must necessarily balance. Well, that's an easy application of the principle of sufficient reason. I'll give you a more impressive one. The universe is infinite, according to the Renaissance philosopher and theologian Giordano Bruno. Why is space infinite? Bruno says, well, there's no reason for it to stop at any particular place. And it's the same in all directions because there's no reason to prefer any direction. And there's no reason to prefer any point to any other point. And therefore, space is infinite, and there are infinitely many stars and infinitely many planets around them, and so on. Now, the greatest advocate of the principle of sufficient reason was a very great mathematician and philosopher Leibniz. Leibniz said, it's the principle of sufficient reason, along with the laws of logic, that God used in making the universe. God made the universe to be the very best possible, with the simplest possible laws, according to the principle of sufficient reason. And if the principle of sufficient reason is true, according to Leibniz, we human beings can figure out scientific laws just by means of reason. I know that's not what they taught you in your science courses, but this is a view that Leibniz took. And I want to give you a very striking example from physics, where a very important scientific law was discovered by the principle of sufficient reason. Newton's first law. Well, we call it Newton's first law of motion, but it was formulated first 50 years before Newton, independently by Descartes, whom we've met already today, and Pierre Gassendi, French guys. The first law of motion says a body in motion with no forces acting on it continues in a straight line at a constant speed. Why does it do that? Well, it goes in a straight line because why should it change direction? All the directions are the same. Principle of sufficient reason. It goes at a constant speed because why should it speed up or slow down? All the points in space are the same. There's no reason the body should prefer being at one point instead of another. Now, Newton himself doesn't mention this argument that I just gave you from Descartes and Gassendi. He doesn't mention this argument at all. For him, remember, the first law of motion is an axiom. But it was first stated by philosophers, and it was derived from the principle of sufficient reason. Okay, so that's a good enough introduction to the principle of sufficient reason. Now let's go back to the question of proving the uniqueness of parallels from Euclid's other postulates. The key big guy here is Lagrange. Lagrange decided, sort of at the end of the 18th century, that he could prove the uniqueness of parallels by using the principle of sufficient reason. And this is from a manuscript of Lagrange that I dug out of the Institute of France in Paris, so you may not have seen this. But anyway, here's what he's going to prove. That through an outside point, there is only one parallel. There can't be any more. And how is he going to do that? He said, you can use the principle of sufficient reason in a mathematical proof. Why? Well, it's just as obvious, Lagrange says, as the laws of logic. So let me show you what he did. Given that we have one parallel, suppose there's another parallel through point P. It would look like this. But by the principle of sufficient reason, there's no reason that this new parallel line should be below the point P on the left and then above the point P on the right. Lagrange says it could equally well be drawn the other way, like this. The principle of sufficient reason says there must be another symmetric parallel line that goes the other way. Lagrange then repeats this exact same argument for lines symmetric to his new parallels. So you're going to get a third line on the other side of his new parallel, and it will look like that. And so on, with lots and lots more, until it goes all around a circle. And here is Lagrange's own picture from his manuscript of the final situation. But this, Lagrange says, is absurd, and therefore the assumption that there's more than one parallel must be false. Okay, now Lagrange never published this manuscript. Maybe because he came to see that by assuming that space is the same in all directions so that his new parallels are symmetric to the old ones, he was assuming the very Euclidean nature of space that he was trying to prove. But it's still important that a great mathematician like Lagrange linked sufficient reason with the necessity of space being Euclidean. Now, it matters for physics. Newton insisted that space must be real. The reason Newton insisted on that is that we can distinguish real accelerations, therefore, accelerations with respect to space from apparent ones. Real accelerations involve real forces, and Newton wants that because he wants to argue that gravity is real. It's a real force. But that real space for Newton has to be Euclidean, and the reason is that using parallelograms of forces is essential to Newton's physics. It's essential to the basic things in Newton's mathematical principles of natural philosophy, It's the theory of parallelograms is involved in his proofs that the planetary orbits are conic sections when you have an inverse square force. Okay, you can't do the properties of parallelograms without Euclid's theory of parallels, and therefore without Euclid's parallel postulates. Okay, let's go back to Leibniz. Leibniz disagreed with Newton about space. Leibniz said there's no such thing as space at all. All there is just the relations between bodies. But Newton's view that space is real won in the 18th century. Okay, I quote an authority whose name you will recognize, Euler. Here's what Euler said. The straight line constant speed motion of a single body with no forces acting on it, according to Newton's first law, that motion cannot possibly depend on where other physical bodies just happen to be at some particular time. It's got to be a straight line always, therefore it's got to be a straight line with respect to something absolute and unchanging, and that is space. So space is real. Even some of the most radical mathematical thinkers, well into the 19th century, believed that there was no alternative to Euclid. William Rowan Hamilton invented the quaternions. That's the first algebra in which multiplication is not commutative. That was pretty radical. But on Euclid, Hamilton followed the party line. He said, quoting Hamilton, "No candid and intelligent person can doubt the truth of the chief properties of parallel lines as set forth by Euclid in his Elements 2,000 years ago." Okay, one more very important person to talk about, the German philosopher Immanuel Kant. Kant argued that space is real, but he said it exists in our minds. It's an intuition of the intellect, and we each have the same unique space in our minds. And we order our perceptions in both time and space, unique intuitions of the intellect. And for Kant, that space is Euclidean. Now, Kant cares about this because he wants to establish that we can come to know non-trivial truths about non-material things, calls them synthetic a priori judgments if you know the philosophy. Example of a non-trivial thing that we know about non-material objects: the sum of the angles of a triangle is 2 right angles. And to illustrate this example, he gives us Euclid's proof, and I want to show it to you. You're given a triangle ABC, you want to show that angle A plus angle B plus angle C add up to 2 right angles. How do you do this? Well, first you make a construction. You extend the base of the triangle BC to D, then you construct the line CE parallel to AB. And then you prove the equality of various angles. I think you're probably all familiar with this proof, but you notice that he is using the theorem that I stated before, the first theorem that needed the parallel postulate for its proof that if you've got 2 parallel lines like AB and CE, the alternate interior angles are equal and the corresponding angles are equal. And so you prove that the sum of the angles of the triangle is 2 right angles. But it's not the details of the proof that matter. What matters to Kant is this: the proof cannot work unless and until you make those constructions. You can't just sit there and look at the triangle. You got to extend the base and make that parallel or something equivalent. Well, where did you make those constructions? Well, you didn't make them on paper. Geometry is not about physical triangles. You made them in space, Kant says, the space in your mind. And since he uses that theorem about if 2 lines are parallel, those angles are equal, the proof of that theorem explicitly requires the 5th postulate. Therefore, the sum of the angles of a triangle that requires also that space is Euclidean. Because this argument is so central to Kant's philosophy, although he doesn't say that space has to be Euclidean, he does say that there's only one space. The space is unique. So, if the parallel postulate is true in it, for Kant, no alternative to Euclid seems conceivable. Well, one more philosopher witness to Euclidean space is Voltaire. Voltaire shares the widespread 18th century idea that universal agreement is a marker for truth. So religious sects disagree about many things, and Voltaire says when they do disagree, that means they're all wrong. Only when they all agree is what they say true. Where do they all agree? Well, they all agree, Voltaire says, that you should worship God and be just. And then he says there are no sects in geometry. One doesn't say, I'm a Euclidean. So mathematics shows that if you demonstrate the truth, the whole world will be of your opinion. And he also said, there is but one morality, as there is but one geometry. The art and architecture of the early modern period also reflect the Euclidean nature of space. Art and architecture reinforced the Euclidean intuition of space in the minds of everyone who looked at the art, the paintings, and lived and worked in the buildings and public squares from the Renaissance well into the 19th century. Perspective in art based on Euclid's geometry helped make Europeans literally see space as Euclidean. This is the first important perspective painting of the Italian Renaissance, the Trinity by Masaccio. Now, you got to get out of our modern mindset to see how miraculous they thought this was. We look at pictures that look three-dimensional all the time because we got photography and television and computers like the one you're looking at this in. In the Renaissance, they didn't. So this kind of painting was very exciting to them. And the realistic illusion of depth in Renaissance art comes explicitly from geometry. I'll show you a couple of medieval European paintings so you can see what the contrast is. All right, this is a picture of some people who are standing in a castle looking at a comet. You notice that the castle is exactly the same size as the people. This is Moses and the children of Israel crossing the Red Sea. Notice that the Red Sea and the people are the same size. When you look at Renaissance art, you're in a different space. In fact, the geometry used in creating Renaissance art is literally Euclidean. It comes from Euclid's Elements of Geometry and from another book we have by Euclid, which is called The Optics. Among the things Euclid proved in his Optics was this proposition: parallel lines seen from a distance appear to be an unequal distance apart. This is not Euclid's diagram, obviously. I guess everybody's muted because I didn't hear anybody laugh, but okay. This theorem is from Euclid's Elements. If a straight line is drawn parallel to one of the sides of a triangle, it cuts the other two sides of the triangle proportionally. And this theorem, the proof of this theorem, logically depends on Euclid's fifth postulate. I want to show you very rapidly how this theorem lets you see the three-dimensional reality on a flat canvas. This is from Alberti's description of how to do it. The parallel horizontal lines that are perpendicular to the plane of the picture are drawn to meet at a point V, which is called the principal vanishing point. That's what you have to do to make it look three-dimensional. This diagram shows the Alberti construction for two parallel railroad tracks perpendicular to the plane of the screen. Now, the checkerboard construction in the Alberti diagram is used a lot in Renaissance painting. I want to show you a couple of examples. Look at the checkerboard floor here. Look at how much bigger the people are in the front of the diagram than the people in the back. And you notice the lines converging towards the figure of Jesus. Here's a more famous Renaissance painting that illustrates the same thing. On the left, Leonardo da Vinci's Last Supper. On the right, with the lines focusing on the principal vanishing point on the face of Jesus to show that he's the center of this painting. Okay, these are Italian examples, but these ideas spread northward throughout Europe. Here's the great German mathematician Albrecht Dürer showing you how to draw something in perspective. Did artists need to master all of this mathematical theory to draw in three dimensions? The answer is no. All they had to do was find the right books. See, Leonardo, the picture I showed you, Leonardo and Piero della Francesca, they were not only artists, but they were also mathematicians. But Dürer's student, Erhard Schoen, wrote a book which has this picture placing models on a perspective grid. He said, you want to draw in perspective? You don't have to learn a lot of geometry. Just look at my drawing and you'll know what to do. Even something that we might see as a non-Euclidean space, namely the reflection of objects in a spherical mirror, where parallels are not everywhere equidistant, are treated by the English artist Turner, who is a master of perspective, as just one more problem in Euclidean geometric perspective. Okay, summing this all up. Since the Renaissance, this is a great Renaissance painting. Since the Renaissance, objects in a painting look the way an objective observer would actually see them, in a rational order created by Euclid's geometry. The art helps teach us to see our world as Euclidean. And one more little point here. Architecture teaches us to see our world as Euclidean. Whenever I talk about this, I'm in a room. I don't know where you all are, but let me show you some rooms. These are both in, the one on the left is in 20th century United States. The one on the right is in China. The one on the left is an ancient Roman house reconstructed in the Metropolitan Museum of Art. The one on the right is a school in Istanbul. So usually we're in a room like this. The rooms are full of parallel lines, which are everywhere equidistant. You see them making equal right angles with the floor if they're on the ceiling, if they're on the walls, or with the walls when they're on the ceiling. If you wanted to brainwash people into thinking that space is Euclidean, you would build rooms like this. But of course, we also build rooms like this because buildings would fall over if walls weren't built according to the principle of sufficient reason. Perpendicular to the ground, which means leaning neither to the left or to the right. I found this picture of some Turkish towers illustrating that leaning neither to the left and the right is the way to make a stable building. The physical spaces that we create for ourselves tend to be Euclidean. The law of gravity demands it. Symmetry demands it. Sufficient reason demands it. Okay, so here's the 18th century European world, the world of sufficient reason, balanced, based on self-evident and necessary truths, embedded in Euclidean space, and we can figure it out all rationally by ourselves. There is a universally agreed upon model of perfect intellectual authority, and that is Euclid's geometry. Okay, this is the end of part one of this talk. Now, part two is going to blow this all out of the water into a different world. It's really amazing that in the early 19th century, Gauss, Bolyai, and Lobachevsky, the three independent discoverers of the first non-Euclidean geometries, or if you prefer, the three independent inventors, were able, in spite of all this Euclidean brainwashing, to imagine that space could be other than Euclidean. And what they did was to realize that the, quote, absurd consequences of denying Euclid's postulate, like that parallels are not unique, like that parallel lines don't have to be everywhere equidistant, that these consequences are not absurd at all, but are truths, but truths in some alternative, counterintuitive reality. In two dimensions. Here's a modern non-Euclidean surface that obeys Euclid's first four postulates, but that does not obey his fifth postulate. So you see the shortest paths on this surface. The red and yellow shortest paths never meet their parallel, the blue one, but nevertheless, they not only aren't everywhere equidistant, they actually intersect. If you look at those shortest paths that cross that central red shortest path, you can see that there are two angles that whose sum is less than two right angles, and yet they never meet. They come together and converge, and then they go and diverge again. Well, still, the idea of non-Euclidean geometry was so revolutionary that Gauss never got up the nerve to publish his work on this subject. As for Janos Bolyai, his father was a mathematician who'd worked on the geometry problem of parallels, and he said to his son, "You should detest, don't do it. You should detest it as you would detest lewd intercourse." Well, Bolyai and Lobachevsky had one advantage. They came respectively from Hungary and from Russia, far from the mathematical mainstream in France, where people were still trying to prove Euclid's postulate from the others. Non-Euclidean geometry required non-traditional thinking, a paradigm change, realizing that the logical implications of denying Euclid's postulate, like the non-uniqueness of parallels, were not intellectual absurdities, as Lagrange had thought, but part of an alternate reality, what Gauss called, this is Gauss's term for the thing he never published, Gauss called it non-Euclidean geometry, as we do. The Lobachevskian version of non-Euclidean geometry is not the only one. There are lots more, as was explained to Mathematician by, among others, Riemann. But wait a minute, what about all that philosophy I was telling you about? Well, there were major philosophical changes to the new geometries. Remember that Kant said that the properties of space are the same for all human beings? And remember that Kant said we humans order all of our perceptions in time and space, and that is Euclidean space? Okay, maybe we can write equations that describe a three-dimensional non-Euclidean space, but can we actually order our perceptions in a non-Euclidean space? Well, yes, we can, says Helmholtz. And this is so cool, this argument. Now look, if we can order our perceptions in a three-dimensional non-Euclidean space, then Kant is wrong. The postulates of geometry are not dictated by the nature of the human intellect or by logical necessity. Then, whether space is Euclidean or not is a question for experience. Okay? So Helmholtz says, yes, by experience, we can learn to order our perceptions in a non-Euclidean three-dimensional space. And if you have never thought about it, you're about to be in it. Look at the reflections in a convex mirror. Now, you probably have one of these on your car. And on your car, there's a little writing on it that says, in effect, warning, the space you see in this mirror is not Euclidean. All right, here's a three-dimensional non-Euclidean space. See the parallel lines at the top and the bottom of the bookcase not being everywhere equidistant. Can we learn to order our perceptions in such a space? Well, if you have a car with a convex mirror, which you have used to change lanes and not get killed, yes, you have been ordering your perceptions successfully in a non-Euclidean space. But you might object. Look, that's a mirror. It's just an illusion, the world in the mirror. Our world out here is real. Helmholtz has an answer to that too. Are you really that sure? How can you tell which world is the real one and which is just the reflection of the real world in some crazy kind of mirror? Well, Helmholtz imagines you're talking to the guy in the mirror. He's a very tall guy, the guy in the mirror. You say to him, my world is real and yours is distorted. He says, how can you tell? You say, well, in your world, when you get closer to the mirror, you grow bigger. And when you get farther away from the mirror, you get smaller. And that violates the obvious Euclidean fact that when you move something around through space, it stays the same size and shape. The guy in the mirror says, oh, let me try that. So he takes a meter stick. He comes up near the interface between his world and ours, and he measures himself with the meter stick. I'm 2 meters tall, he says. And then he goes off to the back of the room, far away from the mirror, and he measures himself again. No, you're wrong, he says. I'm still 2 meters tall. And you say, oh, but your meter stick changed its size also. And he says, ha, that is a likely story. So Helmholtz says, there is no geometrical experiment that you can do that will decide the question of which one of these worlds is the real one. And by the way, if that sounds like relativity theory to you, that is no accident. There is a straight line of historical influence, a straight line, I shouldn't say that. There is a shortest path of historical influence in German philosophy, from Helmholtz to Ernst Mach, and then on to Einstein. And there's an even more radical point of view. This comes from the great mathematician, physicist, and philosopher Poincaré. If, as Helmholtz said, geometry were an empirical science, Poincaré says, then geometry would not be an exact science. Still, Poincaré knows about non-Euclidean geometry. He knows we've got more than one kind of space in our minds. So he says, The postulates of geometry are not unique ideas, as Kant said. They're not experimental facts of experience, as Helmholtz says. And they aren't necessary self-evident truths, as Voltaire and Lagrange said. Geometrical axioms, says Poincaré, are conventions. Conventions. Poincaré says, our choice among all possible conventions may be guided by experience, but as long as we avoid contradictions, our choice remains free. This is a new view about the relationship between mathematics and reality. Poincaré is not the only person to put forth this view. He's the only person, he was the first person I know who put it forth in the context of non-Euclidean geometry. But here is the radical idea that Newton is spinning in his grave at the thought that I'm going to tell you this. Mathematics no longer fits reality exactly, a reality that obeys the principle of sufficient reason. We just choose the mathematical model that does the best job of doing what we want it to do. In the 20th century, it turned out that non-Euclidean geometries of the Riemannian type, that's positively curved space, are what Einstein needed to do general relativity, the theory of gravitation. The paths of the planets moving under gravity are shortest distances in a non-Euclidean space. Light doesn't go in Euclidean straight lines, but shortest distances in non-Euclidean space. Well, you might ask yourself, is space really Riemannian? Poincaré would say, that's what works. We're not talking about reality anymore. We're talking about the model that best fits observation. You know, if we're really interested in what works, there's another set of questions we might want to look at, and that's the psychology of perception, to study empirically how people actually perceive space. Even before there was non-Euclidean geometry, philosophers like Bishop Berkeley and Thomas Reid had pointed out, we don't see distance at all. What we see are visual angles, and we infer the geometry of distance from the angles that we actually see. And I'll give you a very simple but striking example of what these guys meant. This has nothing to do with non-Euclidean geometry. Look at the corner of a room. The ceiling and two walls meet. You look at that and you say, there are three 90-degree angles coming together. But that is actually not correct. If you measure the individual angles as they actually appear, each one's greater than 90 degrees and they add up to 360 degrees. Our visual space isn't the same as the space that we think we see. And the invention of non-Euclidean geometry really reinforced ideas like this and made psychologists think about them a lot more. Remember Helmholtz, our friend Helmholtz? He did an interesting experiment where he asked people in a dark room to arrange little points of light that were sitting on a table in front of them. Take these little points of light and arrange them into two parallel lines that get farther and farther away from you. Well, what the people did was they made lines out of these points of light, all right, but the lines got farther apart as they went farther away, as they were farther away from the person who was setting it up. So Helmholtz said that shows that visual space is Lobachevskian. Well, psychologists have been doing more experiments, and the prevailing view now is that the space of visual perception isn't represented by any consistent geometry. My husband studies Banach algebras and Banach spaces, and even they have been invoked to try to describe the space of perception. They don't work all the time either. Okay, this is all European material. Might ask what goes on in other cultures. The modern cultural linguist Stephen Levinson asked this question: is Kant right? Are spatial categories direct projections of humanity's shared idea of space? No, Kant's wrong again. This time from an anthropological point of view. In language and concepts, people in different cultures have other ways of ordering their perceptions than in an external Euclidean space. Some cultures do use the idea of a fixed coordinate system in space, like Newton's idea of space. There are Native American cultures that have 4 cardinal directions and everything is done in terms of them. But other cultures order their perceptions in space like Leibniz's idea that what matters is the relationship between bodies and only the relationship between bodies. So as you might say, I parked my car to the north of the building. If you're using a fixed coordinate system, you might, if you're a Leibnizian, say, my car is parked to the right of the building. That's from your point of view, relations between bodies. Or you might leave yourself out of it too and say, the car is in front of the building. No coordinate system, no observer necessary. In our own society, GPS navigational systems have changed people's supposedly innate intuitions of space from the Newtonian to the Leibnizian. Tell you something happened to me. About 15 years ago, a cab driver picked me up at the airport in Baltimore, and he told me he just recently bought a GPS system. And I asked him, did the GPS system change the way you think about space? And he got really excited about the question. And he said, yeah, I used to have the whole geography of greater Baltimore in my head. I don't anymore. Now I think about each trip I take. It turn left out of the airport, take the expressway to such and such exit, then turn right. And when I leave you off, I'll just reverse those turns and I'll get back to the airport. But I won't know where I've been. Oh, that's really, really cool. What have modern theorists of culture had to say about this paradigm shift, about the new geometries, about relativity? Well, one very interesting thinker on this topic was the Spaniard José Ortega y Gasset. Ortega used the new geometries to argue that provincialism, assuming that our own experience, our own values are universal, is wrong. Euclidean geometry, Ortega says, was provincial. It was an unwarranted extrapolation of what was locally observed to the whole universe. Instead, says Ortega, reality organizes itself to be visible from all viewpoints. He continues, Einstein's theory of relativity, which requires new geometries of space-time, promotes the harmonious multiplicity of all possible points of view. Now, that's not just true for mathematics and physics, but also for politics and culture. Ortega says this, there is a Chinese perspective that is fully as justified as the Western. Let's now turn again to architecture. I'd like you to think about Zaha Hadid, the modern Iranian architect who was the first woman to win the Pritzker Architecture Prize. As an undergraduate, she specialized in mathematics. We're not in the Renaissance ideal city anymore. Well, imagine walking into this house through that little red door in the middle. Here is what Zaha Hadid says about the world of the 21st century. The most important thing is motion, the flux of things, a non-Euclidean geometry in which nothing repeats itself, a new order of space. Now, these new geometries have inspired many other types of artistic freedom. I'm going to give you a couple of examples from Cubist art of what Ortega called reality organizing itself to be seen from all points of view. Look at the teacup. Well, you can look at this whole painting, but focus on the teacup. You see the reality simultaneously presented from different points of view. Here's a famous portrait by Picasso. Again, there's planes and angles from multiple points of view, and there's no space in that portrait at all. Okay, now I'll show you another different kind of geometrical influence on art. Around 1900, mathematicians began using physical models to teach and study the geometry of non-Euclidean surfaces. Here are pictures of such models. The saddle shape in the upper left is a piece of the infinite non-Euclidean surface I showed you before with the threads on it. It's called a hyperbolic paraboloid. I call your attention to the helix on the left. Call your attention to the surface is made up of lines, of straight lines, of wires. Okay, sculptors looked at these things and they were blown away. Here is an example of art directly influenced by such models. a sculpture representing the world. Here's one whose title makes clear its mathematical antecedents. I mean, these guys are important 20th century sculptors. And here's just a lovely piece by Man Ray, which is called Lampshade. You see how he's used the helix. Okay, well, we know that Man Ray, for instance, studied the mathematical models that I showed you at the Poincaré Institute, because his friend, the surrealist artist Max Ernst, said to Man Ray, you should go and look at those mathematical models, physical models in the Poincaré Institute. And Man Ray was blown away, and he said, these shapes were so unusual, as revolutionary as anything that is being done today in painting and sculpture. Just to show you a piece of Max Ernst art and the influence of non-Euclidean geometry on him. Those are sketches on the right, and that's the finished painting in the middle. And you see the face of the fly. You see the fly from it multiple times at once, and you see some non-Euclidean surfaces sort of lurking in this. So artists are influenced by the new geometries. They cite the authority of geometries and the prestige of geometries on their behalf. They use it as part of their creation of self-consciously modern art, and they help us see a different world. Okay, coming now to my last set of slides. Here's the first. I found this searching Google image for hyperbolic paraboloid. I like this picture because it shows that non-Euclidean geometrical objects had become part of the general culture in a medium-sized American town already more than half a century ago. The mathematical properties of this particular non-Euclidean surface make it very attractive to builders because you can construct it out of lines and because the main stress is compressive stress, so you can make a roof very thin. And to reinforce this point, I'll close this section of the talk with an example that became world famous. The Olympic Velodrome in London, the roof is a hyperbolic paraboloid. Revolutionary ideas about geometry have indeed transformed the world that we all live in. Okay, conclusion. The American mathematician Morris Klein once said, non-Euclidean geometry knocked geometry off its pedestal, but also set it free to roam. Well, the freedom that geometers claimed for themselves was magnified greatly when philosophers and artists picked up their ideas. Twice in history, first in Euclid's world and then in the non-Euclidean world, ideas about geometry have shaped art and architecture, have shaped physics and philosophy, and have shaped the way ordinary people see and think about the world. The first time Euclidean geometry and the principle of sufficient reason came to mean reason can figure out the whole universe, and it's symmetric, and it's stable, and it's uniform, and there's a reason for everything, and everybody who studies it will come to agree. Well, that's not the world we live in now. And the creation of non-Euclidean had a lot to do with the way all of us think about the world that we do live in. Thank you very much.
Thank you. Thank you. Maybe we can applaud or give reactions on Zoom if you are
Well,
willing to do that.
if people have questions, that's cool.
And we have time for some questions and comments. And
I have some questions, if you don't mind.
Sure.
So thanks for the nice talk. I want to ask, I mean, we have seen some natural and direct applications of these geometrical aspects to visual arts, but to what extent or in which sense the literature was affected or has been motivated by these geometrical perspectives?
Well, it's hard to think of well, I mean, there are novelists, science fiction, and stuff like that that use things like that. But if the idea of multiple perspectives is picked up by literature, that's why I started with that quotation from Ortega, because he is talking about literature as well as about the visual arts. I couldn't give you a short story, as part of a talk like this. I think that one of the things that non-Euclidean geometry is culturally is a part of modernism, which Ortega's statement just essentially gets that. If you read novels with multiple narrators and different points of view, if you look at the Japanese movies with the overlapping thing, all these people looking at the same reality, seeing different things, this is part of this sort of general cultural thing. And I've heard people say about modern music, where your idea of a theme and variations and things that come back to the key that it started in, which are Euclidean in a metaphorical way, and modern music is different. The degree to for what I'm trying to do here is to argue that geometry has had this influence, incredible influence on this modernist point of view, but I don't want to claim it's the only thing. And so if you look at the difference between traditional 18th century ideas about space and literature and the universe and modern ideas, you see all these other similarities. I was pulling out geometry as a causative factor because I think that's kind of a novel thing to do. And what started me on this in the first place was I was reading Lagrange's manuscripts in Paris, and I ran across this, and I said, "Gee whiz!" And it seemed so to capture the 18th century thing and to be so wrong. I mean, the proof's wrong, and figuring out what's the matter with it is realizing how internalized these ideas were in the 18th century. And so that's how I got interested in this in the first place. And I gave a talk about this to some art historians, and they said they knew this, but they didn't know any theorems in non-Euclidean geometry before. Thank you for the question. That was cool.
Thanks for the talk again. Thanks.
I put a couple links and comments about some specific authors in non-Euclidean geometry, but
Thanks.
there's a lot more that you can find. Any other questions and comments?
Oh, Lovecraft. Okay.
Sorry, may I ask?
Yeah, sure.
This is David here. Hi, yeah, thanks for speaking. Yeah, there's a lot of things going on. I'm just maybe what you said about Poincaré is the key idea I might ask about. Aren't you describing the breaking free of mathematics from physics?
Yeah, I think that Newton really believed that the mathematical principles of natural philosophy, he had found the law of the universe. I think he really believed that. And he's not the only person who really believed that. And starting with statistical mechanics in the 19th century, where the gases behave according to Boyle's law and so on, but the individual particles are doing whatever, and you can't track an individual particle. And then with quantum mechanics, where the same question about we've got probabilistic descriptions, what's going on, really put your finger on that electron and see exactly, so yeah, I think that's true. And non-Euclidean geometry is just one example within the relationship between mathematics and physics, where we're now thinking about it differently. I agree with that point completely. And I'll tell you, I saw this whole cultural shift happen once in the classroom. I passed around the convex mirror because, the students don't all drive yet, so that they could, and this guy had the convex mirror in his hand, and he's putting it towards his face and then pulling it back and looking at his own reflection in it. And he says, "This is distorted." And one of the other students said, "You are a Euclidean chauvinist." And this just captures this thing that Ortega said about privileging your own nearby experience. I just thought that was cool. I mean, that didn't speak to your point, to your deep philosophical point about the relationship between mathematics and physics, but that was a cultural anecdote I just felt like sharing. But you're absolutely right. And people talk about pure mathematics. It doesn't have to have anything to do with reality, and that's kind of new. I mean, we say geometry, and we think that's something like super abstract. Well, the Greeks said geometry means earth measurement. You're out there on the flat Egyptian plain and figuring out the area of a field. And mathematics and the description of the observable physical world, I mean, they grew up together. They grew up together, even the Greeks, who were philosophizing all the time. There's mathematics in many different cultures, and they all use it to solve problems that in the real world that the culture thinks are important. So this really is a break with a lot of human history and a lot of contemporary human culture even. Thank you, David.
Okay.
Did I answer your question to your satisfaction?
Sure. Maybe quickly, I've seen the Renaissance described as the breaking free of, say, art breaks free from religion, for example, or
That's
science
true.
breaks free. So, I mean, this is still part of the Renaissance process. It seems to me that it's carrying on to the 19th century with now all the different fields coming into their own. But yeah, it still means a kind of disjointedness that
Well,
that goes back to to the Renaissance. But, yeah.
Well, this is not the only big break in historical consciousness. The Renaissance, the infinite universe, that was a big break. The idea, the universe can't be infinite if the Earth is at the center and everything goes around it. So Copernicus makes it possible to set it free. But the idea of the infinite universe is independent of Copernicanism. I mean, Giordano Bruno's idea is that Pascal wasn't sure that Copernicus was right, but he believed in the infinite universe. So there are lots of cultural breaks, but I was focusing on this one. But yeah, deep, profound. Who was it who said this? I can't remember the guy's name. He's a novelist, but he says the past is a foreign country. They do things differently there. I think that's true of the history of the ideas I was talking about. Book's called The Go-Between. I just can't remember his name. Anyway. Okay.
Thanks. Mm-hmm.
It was very interesting to point out that those of us who are into pure mathematics kind of owe our existence, right, to this break from physics, as David has said, and from necessary universal truths, as you have brought us to think about. Any other questions and comments? Thoughts? while we have Judy here for a couple more minutes, please use this opportunity. She is a fountainhead of ideas and knowledge. So, and she makes a lot of connections. As you have seen, she can make a lot of connections in like instantaneously. So any thoughts and comments that came up?
Well, Judy, how much do you think Jorge Luis Borges was affected?
Oh gosh, yes. All right. Yes. I think he's in the same cultural space as Ortega, and yeah, that and the mystical religious sensitivity, which is of course a whole other thing. The use of infinity and the use of combinatorics to the use of a piece of mathematics to show that the world doesn't make any sense. I think that is that's Borges does that, and it's hard to imagine Lagrange even sitting still to hear that. Okay, you're frozen. You want to unmute and say something back?
Well, no, I mean, I wondered how much quantum mechanics and, Heisenberg and Borges interacted with each other.
Well, I mean, one of the facts about mathematics and its influence on culture is that people, and physics too, everything, that people can be influenced by it without understanding it completely and without being masters of the ideas. And Newton thought that his physics could help people become more religious. And so a guy called Richard Bentley, who was a theologian and contemporary of Newton's, used Newton's Principia to prove the existence of God. And and I think it's fair to say that Bentley could not have proved one single result from the Principia, but he got this idea of order, and sort of, if I may say so, deified it.
I see. Thank you, Judith.
All right. We're coming to over an hour and 10 minutes almost, right? We have taken a lot of your time. Any other last minute questions and comments? Otherwise, we should probably wrap
Well,
things up.
I want to thank all you people from wherever you are for coming to listen. And this is in print if you want footnotes in the American Mathematical Monthly 2000 something. It won this article won what is it? What is it? The Lester Ford award for one of the best articles in the American Mathematical Monthly. And I mention this if you want to see footnotes and sources for some of the things that I used. And I got to say, it cost a lot to reproduce that Escher print. You can't just go around reproducing Escher's prints for free. So, but you all can buy a convex mirror.
Yeah.
Okay. Well, thank you very much for inviting me, and everybody.
Thank you so much, Judy. Let's thank Professor Grabiner again, and thank you all for being here and staying till the end. Great questions. Thank you. Thanks again, Judy. Thank you. This was awesome.